All right, so I'm Michael Amexon,
Sullivan Jones.
I'm Brandon Barr.
And I'm Rafia Chowdhury.
and this is our presentation on our solar battery charger. So the background of our project is
This research examines the application of a solar panel charging system that is used as means of charging or storing supplied power for power loss. The system's aim is to collect the generated light captured from the artificial light cells in McNair's hallway to obtain a sufficient amount of power to charge the 10-inch Android tablet. The compiled report is delivered to their customer as a method to ensure that the information displayed on the tablet is never available due to a lack of charging the device.
so the general background for our project is that have you ever went to a professor's office hours and they were not there? So the issue that we're having here is professor's office hour times and the professor not actually being at their office hour at that time. So what we have created here was we have a tablet which has preloaded software where you can actually go in and sign in and actually look for office hours appointments. And basically we came up with a solar battery charging system that will keep this tablet charged for a minimum of 12 hours.
Okay, so just a brief overview of what we'll be covering today. We'll go over the requirements that we developed for this project. We'll also go over how we designed it and some of the details of that. We'll go over what happened when we tested it, and of course, you'll be able to see the entire project plan as this entire project pulls out.
All right. Marketing requirement number one: the solution should be dependable. So we want to be able to apply for 12 continuous hours. Especially we don't want our tablets to never run out of charge. We want it to always be accessible during the period of the day and during working hours. We also have sufficient current supply from 7 a.m. to 7 p.m. We chose those times because those are the period of times that sometimes professors come in early and sometimes professors leave later. So I think that would be that's a good 12-hour period to keep have our tablet charged and be accessible to the students and the professors.
Okay, the second marketing requirement was that the solution should not appear stout. Really, we don't want a hazard of wires just running through crevices and doorways because that can create all types of problems. So that's one of our engineering requirements. And the other, of course, we don't want to have cords running in nearby outlets just because it looks sloppy.
Okay, so our third marketing requirement is the solution should not need extraction for charging. For charging. So basically, what we have here is our solar battery charger, and just in case it has some malfunctions or something where we need to replace something in the system, we don't actually want to have our solution being disabled, not to be able to move or disconnect it from the door.
And the fourth marketing requirement is that the solution should be sustainable. It must be easily dismantled from the door mount to be replaced, and it must be efficient and maintainable.
So here is our UML diagram, and so generally we just have our solar panel system, which is going to generate this photoelectric energy, which is going to provide power to our whole system. Then we have our user, which is another actor, which is going to act upon our system, where you go in and actually look at the professor's office hours. You have our battery switching unit, which is also an actor in our system, which basically just controls the overflow of current and maybe if there's not enough current. It's also consists of a bipolar transistor that we're going to use as a switch, and also a relay to charge the tablet battery or to not charge the tablet battery depending on the battery life. So we also have our power bank, which is also another actor in the system, which is going to provide the energy stored, and it will also charge and recharge itself. So here we have our basic circuit diagram. We have our solar panel, which we have here our 24 volt source. It's going to, we're going to use some diode to forward the current to run into this voltage regulator. This voltage regulator has an input, output, and adjusting pin, so therefore we can adjust the voltage drop over here so we can get what we need necessary to charge our portable battery. And then what we have here is once our portable battery charges, we have the Zener diode, which is going to detect current overflow for this battery right here. It'll then send a current to the gate or the base, and then it'll actually ground our regulator to stop charging. So here we also have a relay switch, in which the sense of, for this tablet battery, as we use as a capacitor here, this tablet battery will charge when the voltage has gone low. That's what the relay switch is for. The relay switch will detect when it has a low voltage on the tablet, which will then either switch from normally open to normally closed, which allow us to charge our tablet battery.
Threshold, when does it trigger? What level of voltage do you know?
We haven't got that far in our testing process yet.
But for our testing, like we've been working with 12 volt relay triggers. Yes. So yeah, this is this is a overview of our testing procedure that we're trying to go through. We have two different types of tests that we've been working with, hardware and software testing, doing some simulation. This particular test, you can do, we created a breadboard where we kind of design that same circuit up there using the capacitor and the transistor, basically exhibiting the functionality of our switching unit. This test will show you how the power source will charge up the power bank, which is exhibited by the capacitor, and the capacitor will charge up the tablet battery, which is also exhibited by a large capacitor. These are super capacitors that are exhibiting these batteries. This is great for testing because you can quickly charge and discharge these capacitors in a period of time. Again, our steps in the hardware aspect, you will turn on your 15 volt. You turn on your 15 volt power supply. It has to be between 15 and 24. You turn on your multimeters. You have 3 multimeters that you will have to work with. One that's over the tablet capacitor. One that's over the power bank capacitor. One that's showing you the voltage across the one that's indicating whether the Zener diode has started to conduct in a reverse direction, which is to the continuity between the emitter and the collector on the transistor. What we want to see is we want to be able to show you the potential across the power bank. You should be able to see that potential rise, and then you should be able to, it should only rise to a constant value, and then it should stop charging. Because once it reaches the Zener diode breakdown voltage, the Zener diode will then start conducting in reverse direction, which will turn on the cutoff switch for the charging mechanism. And yeah, you wait until you hear the signal beep, the continuity from the other voltmeter. That will signal that the Zener diode has started to reverse, conduct current in reverse direction. And then that's the point that you should see the capacitor start to be at a constant voltage until the tablet battery begins to charge from that capacitor, which we will show you in our demo today.
So this is the cost summary table. Basically, we have, the first one is the solar panel, and those are mini polycrystalline, so we have about 20 pieces. And then we have a power bank, the 25 logo, and that one is about $279. And then we have a transistors bipolar, a 12 volt, 24 volt DC, and a voltage regulator. So that's pretty much the breakdown.
Okay, and as far as the work breakdown structure and the project plan, we represented it as a Gantt chart. And as you can see, really a lot of the time is spent on the preliminary design as far as research, the layouts for electrical and hardware, and of course purchasing supplies and making sure they get here on time. The next general step was the construction of it, and we broke it down into components, setting up the switching unit, the solar panel system, the power bank, and everything. And these things are somewhat independent of each other, so we can work on these things simultaneously as a group, while once everything's finished, we literally just connect them all and leads to the next step of testing, which we're really just testing each individual component to make sure it's doing what it's supposed to do. And really, once we've tested the major areas, we just make modifications if necessary, and from there, the entire thing is summed up.
So therefore, we went over our marketing requirements for our project, which is simply just the outlines that we have from our customer. Our design, we basically showed you our circuit design of our battery charger, which we'll be using furthermore for the rest of the semester. The testing we have undergone some other issues, so we're still in the research stage, and we're also still testing to get efficient amount of power for our system. And for our parts, we're in the process of purchasing our parts, but what we want to do is make sure that we have the exact parts which correlate with our exact voltage. So we're still going through some testings for that too.
Okay, at this point, we're going to open it up for any questions you have.
Have you done any simulation of these?
Yes, yeah, we'll show you that now.
Yeah, the result of-
Yeah.
So your timeline to put it together and do the actual thing testing, when is it planned?
Well, we have already done testing in simulation wise. We done half the testing for the hardware, so that's already something we've begun. Now we just want to fully test it on the breadboard. So hopefully we can have that done within the next week. We can have that fully tested on the breadboard using actual solar panel.
Therefore, we could start applying it to our system, knowing the way that it works and knowing the voltage, the outputs that it's going to get, and we can actually build our. We can use the parts that we ordered to actually construct the same exact circuit.
So basically, you by end of this month, you should.
So probably around by the end of this month, we should have something pretty solid and steady. So now we'll show you our demo.
Where's the?
Oh, wow.
How you doing?
Good morning.
Good morning.
Yeah, thank you. I don't want to, this is circuit here for our simulation. This is the exact circuit that we built that we came up with for our particular design. As Mike was saying, you have your voltage source here, and then you have your voltage regulator here. So you have your unregulated voltage source coming into a voltage regulator that's adjusted by these two resistors here, and then the outputs are regulated voltage. In this particular simulation, it's outputting around maybe close to 16 volts. Just for arbitrary reasons, so you can quickly show you certain results. And as you saying, you have have the Zener diode here, and you have your capacitor here. This Zener diode is rated for 13 volts. So once its potential over this particular supercapacitor reaches a certain voltage, once this node hit that voltage, this Zener diode will then start conducting current in the reverse direction. Therefore, sending current here, allowing these to connect. Therefore, basically sending this voltage down here to close to zero, which will in turn make this voltage here stop charging and send that to a constant voltage. That's just representing our power bank. And this here, this representing our tablet battery. This tablet battery will actually charge from this power bank. So this is a 12-volt relay. So essentially, it's normally closed state, meaning the potential across this capacitor is less than 12 volts. This will charge this. Once this goes above that 12 volts, this relay will then switch to the normally off. As you can see, this is not connected to anything, so basically it does nothing. So this voltage will then start to decline, which is representing the tablet losing charge. You can
So as you can see here, what we did was we labeled our nodes to be our battery, our normally open or normally closed switch, and our Zener diodes. So when we run our simulation, these are the output values that we got. So
this is over a pretty long time period. As you can see, this is up to 2,000 seconds. I can see on this side, the capacitor. Brandon, you can hit this button here. Take away that pink line there.
Take away the thing?
Yes. Yeah. Hit that line, and also hit this line here.
Third
CD.
one.
Yeah, right there. All right. So as you can see, this is the capacitor for the power bank. This blue line represents that. This line represents the voltage regulator. This line represents our battery for the tablet. As you can see, the potential on those rises. The potential on the capacitor for the power bank, it rises up to that 13 rated volts for the Zener diode. And then once that Zener diode cut on, as you can see, this capacitor goes to a constant voltage, meaning that it has stopped charging. As you see, this tablet battery, once it reaches that 12, close to that 12 volts, over that 12 volts, it's ready on a relay, you can see that it switches and then it starts to decharge and loses power until the relay switches back on, and then you can see that it starts to charge back up to the voltage again for the that's outputting on this capacitor for the power bank. As you see, at this point in time, when the power bank, you can see this sharp discharge in the power bank, you can see a sharp increase in battery power as well. So therefore, this is showing that while this is discharging, while this is disconnected, this voltage will stay constant until this is reconnected again, therefore taking a charge from that power bank. So essentially, you can say that our solar panel is kind of indirectly charging our tablet. Solar panel is charging our power bank. Power bank is charging our tablet battery. I feel like that would be a better way more efficient way to keep our tablet charged than directly charging it from our solar panel.
we also want to look at also a safer way of doing it. So therefore, we won't provide too much overload of current to our tablet, which can destroy our device.
What is the top line?
This top line here represents a voltage source.
On the solar panel?
Yes,
Yeah.
yeah, the solar panel. So, this, it's so the voltage source. The voltage
So
source.
it's like constant, maybe 20 volts. You can see it. It'll probably drop down maybe to like 19 or something, but it's constant throughout the whole simulation.
And you see the, but these values, this value, this graph represents the results that we were looking for in the charging of our particular capacitors. I'm trying to charge we're representing our batteries down circuit.
The capacitor that you have there is, what is the rating, voltage rating on the capacitor? Is it just 50 volts or?
The capacitor,
Mhm.
well, the capacitor, the voltage rating is not, you can, as long as it's high enough to reach the particular point that you want. So the capacitor that's in the circuit, you don't define the voltage for the capacitor. The capacitor is just going to reach the potential that you give it. Given that it's not, so say you have a 50 volt capacitor and you apply a 12 volt source to it. The capacitor is going to reach the potential of 12 volts.
So it is at the, at least minimum of the tablet, which needs 18